When we have a question like this where we're under non-standard conditions with the temperature not at 298 Kelvin, then the equation we're going to use is this one. Delta G under non-standard conditions at a temperature T. And that's going to equal delta G under standard conditions at 298, and then we're going to correct that with this term plus RT ln of Q. Here. And so what we want is we want this 0.5 bar here as our Q. And so what we're going to do is we know that this is not at 298, sorry. In fact, we don't know what the temperature is, do we? We're trying to solve what the temperature is. I can solve for delta G under standard conditions if I know what the temperature is. But if I don't know what the temperature is, then I can't solve for it, right? Because so in this case, what am I going to do? Well, in this case, I want the delta G under non-standard conditions and the temperature not at 298 Kelvin to equal 0. Because we want it to transition from positive through 0 to negative. So we'll just set it to 0. And that's going to equal my delta G under standard conditions at temperature T plus this correction factor, RT. This is going to be equal to ln of K. This is where K, is the same thing as we had before. This is the H2O gas. So K is the products over the reactants, and since these are gases, it'll be H2O gas over 1. The activity of a pure liquid is just 1, so just K is equal to partial pressure of H2O liquid. Now, how am I going to solve for this? The temperature. Do you guys recall we solved for this?
Yeah, assume that delta G naught at T doesn't change significantly from delta G naught to 98, so you use delta H and delta S.
Okay, delta G naught at temperature T does change significantly from delta G naught at 298. And therefore, they're not close. But the second part of what you said is correct. Delta G naught at temperature T is about equal to delta H naught at 298 minus T delta S naught at 298. And so the reason that the first one, we can't assume that they're close, yeah, the delta H and the delta S are the same. We'd use the exact same delta H and the exact same delta S to calculate delta G naught at 298, but the big difference is the T. The T is going to be totally different, and so that means that the delta G will be totally different. And so what we're going to do here is we're just going to make this equal to delta H naught at temperature T minus T delta S naught at temperature T, not temperature T, temperature 298. This will be temperature 298. And so this is our standard, our delta G naught at temperature T, but we still don't know what temperature T is. And then we correct that by using RT ln of K. And but what we're trying to do is we're trying to solve for T. So what I'm going to do is I'm going to just rearrange this algebraically. So I'm going to add T delta S and subtract a RT ln of K from both sides. Or actually, no, I'll just leave it. I'm just going to make this T is equal to delta H naught. I'll leave this as positive here. Divided by, and then factor out the T. Do you remember doing this the other day? So add that, subtract that. So this is going to be delta S naught minus R ln of K. Well, K is just the pressure. And so this is just going to be the partial pressure of H2O. The partial pressure of H2O is 0.5 bar. That's what we set up here, 0.5 bar. So now we can solve for the temperature. here. And so the delta H naught was 44.0 kilojoules. The delta S naught was 118 joules. Minus R, 8.3145 joules per Kelvin. Times ln of P. ln of P, H2O. This is joules per Kelvin, S. And so we want to make sure the units work out. I'm going to convert this to joules and then solve for the T. So first I'll do the natural log. Just use my phone. .5 natural log times 8.3145, 8.3145 negative, plus 118 equals, and then I'm going to invert that, times 44,000. Oh, I screwed up. Let me try that again. 0.5 L natural log times, unless, did somebody solve it already? .5 Kelvin. So I got 355.5 Kelvin. 82.5. 82.5.
I think the original question was, scroll up a little bit, please. It's in that P, is that P atmosphere?
Atmospheric pressure.
Yes.
Atmospheric pressure, but the units are in bar. Let me rewrite that.
Okay, equals 0.5 bar.
Yeah, 0.5 bar.
And so.
We could say the barometric pressure as well.
And then so does that equal the K that you calculated on the right, which is equal to the pressure of the H2O?
Yeah.
So
Because when atmospheric pressure equals the vapor pressure, then boiling occurs. And so the vapor pressure is going to be the pressure of the H2O gas. It's vapor pressure.
So is it, can I say for any equation that the atmospheric pressure is going to be a decay value?
Yeah, for this, yes, because the K value is the products over the reactants. The reactants is a pure liquid, so the reactants is just 1, and this is a gas, so K is going to equal the partial pressure of that gas. If this were a solution, then K would equal the molarity of the gas. Of the solution.
Okay, for sure. And then one below the pressure. How would I know in the future that delta G of temperature is equal to 0? Is that just because the reaction happened? So obviously it went to equilibrium.
The reason we're setting it equal to 0 is because the first term is unfavorable. It's going to be positive. And so what we need to do is we need to cancel this out by having this one equal and opposite, negative. And so what we want to do is we want to cancel this unfavorable one out with a negative, which is favorable here. And the way we do it is, how much do we need to cancel it out? Well, we don't have to set it to 0. We can just figure out what this is and then make this negative,
Negative which one?
and then they'll cancel each other out. The easiest is just to set it equal to 0, and then the two sides will equal. Delta G naught is going to equal minus RT ln of K. Does that make sense?
And then just doing that will limit the amount of factors you have to take in to find the temperature.
Yeah, we just use that. We don't even have to find the temperature. For example, I could I could give you the temperature. Let's say I wanted water to boil at 50 degrees C. If I want water to boil at 50 degrees C, then what vacuum pressure do I need? And so if I can calculate the pressure that's needed, so I just plug in. In that case, I use a little different equation because that might be a little bit easier
Yeah.
to solve.
And then so if you want to find that, then the delta G would be 0. And you do a similar project right here, except you just isolate for Q or K,
Yeah,
and that's the pressure of the H2O gas.
yeah. Right.
Okay.
So if you wanted to boil water, let's say I hook this up. I didn't measure the vacuum, but I'm just guessing. If I hook this up to my water beaker in a vacuum jar, I'd have to heat that up to about 82, 83 degrees C, and then it'll boil. Right. But it's boiling at a lower temperature. I didn't really have to do this completely. If I recall back to chapter 12, let's go back to chapter 12. I could have done this much faster. Do you remember the Clausius-Clapeyron equation? Did we talk about that before?
There are a couple.
Yeah, 3 forms of the Clausius-Clapeyron equation. I think it was 533. Do you guys remember this? These? It's back in chapter 12. These are called the vapor pressure curves. And so if you look at water, water's C here. And from the vapor pressure curve, we can easily get the boiling point of water. So let's say we're under normal atmospheric pressure, 760 millimeters of mercury. If we're under normal atmospheric pressure, then in order to get water to boil, the vapor pressure of water has to equal atmospheric pressure. So if atmospheric pressure is 760, then the vapor pressure of water must equal 760. Well, the black curve intersects here. What temperature is that? So we drop back down and we take a look at the temperature, and the temperature is 100 degrees C. So 100 degrees C is the normal boiling point of water, correct? What if we go to about half an atmosphere? Half an atmosphere is about, 380? And half an atmosphere is about a half a bar. If we're at half a bar, what's the temperature, roughly? 80 degrees C. That's what we just calculated, right? In fact, this curve, if you fit this curve mathematically, do you know what kind of function this is? The vapor pressure curve? And there's a relationship here. You know, these calculations that we just did are, if we figure out the vapor pressure of the vapor pressure of the water is equal to, actually, what do we want? We want B. Let me do this. It's just some kind of constant, which we'll call B. This is called the pre-exponential constant. And the curve is, to the minus A, let's say, where B and A are constants kind of thing. And then we have 1 over T here. And so we have a curve like this. In other words, this equation looks awfully like this one here, which is K is equal to e to the minus delta G over R, which is going to be a constant at a given temperature, over 1 over T. Although delta G does change with temperature, let's make that more of a constant. We make this e to the minus delta H, minus T delta S over R, 1 over T. So it has the same form. And so to make a long story short, basically this is our delta G calculation here in K, where K is just the pressure of the gas. And so we have that. So we take the data, these are the measured values, and we make a graph like this. And then we get the mathematical equation that defines this. Although getting the mathematical equation of a curve is more difficult than getting the mathematical equation of a straight line. So we do a logarithmic plot of that data. And it turns out when we do a logarithmic plot, a natural log plot, it comes out linear. And so we have, this is another version of the Clausius-Clapeyron. So that was the Clausius-Clapeyron equation that kind of describes that curve, the vapor pressure curve. That's a mathematical equation. And then it turns out it's an exponential increase. And so a semi-log plot like this would work against 1 over T. And that gives us a straight line. Fitting straight lines is easier, so that's why they converted the curve into straight line like this. And then we can get the constants. One of the constants is delta H. And so it comes out to a form like this, you know. And we had a form like this too. The form like this was L and a K. In other words, L and a P here. Here, L and a P. Although I didn't write it all out. And so this is our L and a K, which is L and a P. Is it up there more? Yeah, here it is. So we have this, K is P. So we have an equation like that. Oops. Which is similar to this equation here, you know, with the intercept. And then we do the trick. This trick is taking L and a P at temperature 1 and T1, and L and a P at temperature 2 and T2, and subtracting them. We subtract P2 from P1, and then we can derive this equation. And so these are 3 forms of the Clausius-Clapeyron. The first one was to define the curve. The second one here was to define this, you know, if we do this natural log versus 1 over T. And the third one is just to skip all the graphs entirely and just be able to calculate. With this equation, we could have calculated this. That is, we want to know the temperature at which the pressure would be 0.5 bar. And so we know at 1 bar the temperature was 97.5, I think it was. 99.5 is what we calculated, the theoretical. And so we plug that in. We know delta H of vaporization. So we didn't even have to do all this thermodynamic. We could have just used the Clausius-Clapeyron equation. Does that make sense? But now we have another way of doing that. And the other way of doing that is we could just use the free energy. And we would, in fact, derive the Clausius-Clapeyron equation from the free energy equation. So these relationships, you might have forgotten about the Clausius-Clapeyron equation, but if you had this fresh in mind, you might see the connection between the Clausius-Clapeyron equation and our delta G and K, because they're the same equation, basically. Okay, any questions on this? And so here we're using a combination, you know, of non-standard conditions and temperature. And so we could either set the non-standard conditions and solve for the temperature, or we can set the temperature and solve for the non-standard conditions. And so let's say I didn't want to heat it more than 50 degrees C. what kind of vacuum would I have to pump? This is not just pressure, but it's also concentration. Rather than doing standard concentration, 1 molar, what if I went up to 16 molar? How's that going to change the driving force? And we can calculate that based on Q. And so those are manipulating that, but oftentimes we're just given it, and we're just given whatever K or whatever delta G value we have. And so what we're going to do is we're going to switch over to chapter 15 now. And actually, did I talk about coupled reactions? No, I forgot to. We're not going to switch to chapter 15 yet. I need to do one more thing. And that is, I need to talk about coupled reactions. This is another way of manipulating our delta G, although it's not perfect because we have to look at what's important, for us. So let's look at coupled reactions in delta G. So one of the reactions that we might be interested in is gold. Trying to get gold to dissolve. Gold is insoluble in water, right? But maybe if we attack gold chemically, we can get it to dissolve. So one of the ways we try to do that is we'll try to oxidize gold using a powerful oxidizer like nitric acid. You might be able to try that out here. And so we'll just inventory this. We have gold solid, H+, nitrate, and water. Gold will be a reducing agent. H+ is an oxidizing agent. H+ in nitrate is also an oxidizing agent. And water is both a reducing agent and an oxidizing agent. Well, this is nitric acid aqueous here. So our strongest oxidizer will be nitrate and H+. And it turns out, do you know what our strongest reducer here is? Turns out we're going to have to use Appendix D because gold is not on the chart I handed out to you guys. Is it on that chart?
No.
You know it? Okay, that's good. But let me show you where you would find it. We go to Appendix D here, and we can find gold. So fluorine is the most powerful oxidizer here. And as we go down, we'll see gold 3. Gold 3 is a powerful oxidizer as well. And its conjugate reducer will be gold metal. And so as far as reducing agents go, we have water versus gold metal. We have water here. And so it looks like gold is stronger, but we also have water a little lower down. In fact, we have water here. And this water goes to oxygen, so it looks like water is stronger reducer than gold. And so when we go back to the equation over here, we would say that. However, do you recall what I was saying about chloride versus water? Water is a stronger reducer than chloride, but we choose chloride. And we choose chloride because mechanistically it's easier. The oxidized chloride is just plucking an electron off a chloride ion. But when we oxidize water, we have to break the bonds and rearrange everything. And not only that, nitric acid is stable in water. Does nitric acid oxidize water? No. If it did, we'd form oxygen gas, but we aren't. And so instead, what we're going to do is we're going to take a look at not water. Water should be it, but we're going to try gold. Mechanistically, gold could be easier to oxidize because all we have to do is pluck an electron off a gold atom. Here. And if we didn't oxidize gold, nothing's going to work. So we're just going to go with gold. And we'll copy the half reaction off the chart here. So what we have is we have solid gold goes to gold 3+. and 3 electrons. So I'll go back over here and write that in here. So the half reaction is solid gold is going to go to gold 3 plus 3 electrons. And then we know that the half reaction for nitrate and 4H plus is on the chart, our standard chart, plus 3 electrons. This is going to go to NO gas plus 2 H2O liquids. In this case, 3 electrons are produced and 3 electrons are consumed, so we don't have to multiply these by some factor. We're just going to combine them straight. And so combining these two half reactions, I'm going to get gold solid here, plus 1 nitrate, plus 4H plus. And then the 3 electrons will cancel. So I have 3 electrons being consumed, 3 electrons being produced, and they cancel. This is going to go to gold 3 plus NO gas plus 2 H2O liquids. So I want to figure out what delta G for this is, but we already know delta G for this is, well, we already know from our Chem 1A analysis what it should be. Because when I look at this, this is my reducing agent, and then nitrate and H plus, this is my oxidizing agent, and this would be my conjugate oxidizing agent over here, and this would be the conjugate reducing agent over here. And based on the oxidizing agents, gold 3 plus is stronger. And that means this must be a weaker reducing agent, weaker oxidizing going to stronger and stronger, which tells us the driving force is not forward, the driving force is reverse. And so there's no driving force in the forward direction. If there's no driving force in the forward direction, then delta G's got to be greater than 0. And we're going to do this under standard conditions at 298 Kelvin. And so delta G on it's greater than 0. Well, what's the easiest way of calculating delta G naught? The easiest way of calculating delta G naught is to use the delta G naught of formation, that is the standard free energies of formation of the products minus the standard free energies of formation of the reactants. So I can find the free energy data in Appendix D as well. So let's go back here and take a look and see if we can find it. So gold is a G for gold. This is alphabetical, so I'm going to go C, copper, F, fluorine, H, A, B, C, D, E, F, G. So fluorine to helium, I should have gold in between here. So gold is missing on this. If I don't have gold here, can I calculate it? No. Not using the delta G's of formation. And then I'm going to look for the standard free energy of formation of gold 3 plus. And I didn't find it on Brave, so I'll take a look here and search it on Google. Let's see if they have it here in a more comprehensive table. Arsenic, barium, boron, bromine, calcium, copper, C, A, B, C, D, E, F, G. So after fluorine, again, G, H. I don't have it. So I'd look for it. And maybe I find it, maybe I don't. But it turns out there are more ways to determine this, and one of the ways of determining this is going to be seen in chapter 19. When we get to chapter 19, what's the page number? We're going to have these numbers here. And so if you look at gold 3 plus 3 electrons yields gold solid, you'll see, do you see this? This standard reduction potential? 1.52 volts positive. Do you know this voltage is related to delta G? That is, when we think about a battery, the higher the voltage, the bigger the driving force or the smaller the driving force? If you have a battery, the bigger the driving force. And in fact, delta G and the voltage can be related by a simple equation. But it's the cell voltage. This is half voltage here, this half cell voltage. And so the calculation is a little bit more involved. We have to do a couple of steps, but we can get the delta G of formation for this based on that. But we aren't going to do that until we get to chapter 19. So what are we going to do in the meantime? In the meantime, we're going to do this. We're not going to calculate the number. We're just going to leave it. That means, are you going to successfully dissolve gold in nitric acid? No. We need something more powerful than nitric acid. But let's say we don't have, do we have a more powerful acid? We do, but not in the laboratory. So we're stuck with nitric acid. We could try boosting the, what can we do next? This is under standard conditions. We could try boosting the concentration. So rather than using 1 molar nitric acid, why not try 16 molar? So if we go to 80 molar, it's not possible. 16 is the most. And so if we go non-standard, then we can take our standard, which is not favorable. This is going to be at 298. This is going to be at 298. And then we're going to bump up the concentration to 16. In other words, before it was 1, now it's going to be 16, which means it's going to be 1/16. 1/16, taking the natural log of 1/16 is going to be negative, so it's going to make it more spontaneous. But you know what? It's not enough. It's not enough. Q here, the Q is going to be kind of weird, because the Q is going to be the product concentration, which is going to be gold 3, and then this is a gas, so it's going to be the partial pressure of NO gas. And then the water squared, and so this will be the activity of water. What is the activity of water? 1, and then we just square that. This is going to be 1 squared. Divided by the activity of a solid. What's the activity of a solid? 1. Divided by, okay, this is going to be the concentration of nitrate, and the concentration of the H plus to the 4th. So what we can do is we can increase the nitric acid concentration and up to 16 molar. And what's that going to do? It's going to increase the driving force. It's going to make this term more negative. But you know what? 16 molar is not enough. It still comes out positive. And so, well, we could try increasing the temperature. So let's go with 16 molar at hot. We call this hot nitric acid. We call it hot concentrated nitric acid. Hot concentrated nitric acid starts fuming, orange fumes. Looks nasty. And you know what? It's not enough. And so we try non-standard conditions. We try temperature, and we're kind of at the limit. I mean, we can't increase the temperature above 100 degrees C because, well, the water is going to boil off, right? Although it's slightly above 100 because of the chelative properties. And so rather than give up on this, you know, there's something else we can try. And that something else that we can try is a coupled reaction. And so it turns out, well, we're going to take advantage of the chemical property of gold. And so this is kind of Le Chatelier's. What we're going to try to do is we're going to try to remove the gold from the first equilibrium here by reacting it. And so what can we do? Well, we could precipitate it out. That's one thing we could do. But we're trying to get rid of the solid. We're trying to dissolve the solid, so I don't want to replace it with another solid. The other thing we could do is this is redox. The other thing we could do is a Lewis acid-base reaction. So let's try a Lewis reaction. And gold is the Lewis acid, and we can try a Lewis base. And we can look this up. It turns out that gold can form a tetrachlorido complex. And we end up with this. How would you name this?
Silver tetrachloride.
It's not silver, I mean gold. Delta tetrachloride? Maybe I'm missing the square brackets. We don't call it gold tetrachloride. We call it something else. What would he call it? Tetrachlorido orate, and the charge on gold is +3. So tetrachlorido orate 3. That's what we call it. And it turns out the formation of this is very favorable. Delta G is quite negative. And so what we do is we add up or combine these. And so we're going to couple these two reactions. And so what we end up with here is gold solid plus nitrate plus 4H plus. Okay, now this gold 3 cancels. So this gold 3 cancels that gold 3. And then we're going to have 4 chlorides. This is going to produce gold 3 plus. Oh no, gold 3 cancels, sorry. Get rid of that. We're going to form this tetrachlorido orate 3 from that plus NO gas plus 2H2O. And the delta G for the net reaction, that is the coupled reactions here, is just equal to the sum of the delta G's of the steps. You know, this is a 2 steps. And so in step 1, the delta G was positive, not favorable. In step 2, the delta G was quite negative. And if it's negative enough, it'll compensate for this positive, and then we'll just end up with a delta G that's negative overall. And so this is what we're going to do. We're going to just dissolve it here. And so we're going to dissolve it in nitric acid. And we need a lot of H plus for this. And so what we're going to do is we're going to use, for the source of chloride, we're going to use hydrochloric acid. And that way we don't have, like, if we use sodium chloride, we're going to have sodium ions contaminating this. We don't necessarily want. And so we're going to use hydrochloric acid. And it looks like we want to use it in what ratio? We want like a 1 part nitric acid to how many parts hydrochloric? 4 parts hydrochloric. And but it depends on the concentration, because concentrated nitric acid is 16 molar. Concentrated hydrochloric is 12 molar. But anyway, something like a 1-to-4 ratio. And then we're going to call this mixture aqua regia. So nitric acid is not enough. Hydrochloric acid definitely won't do it. But a combination of nitric acid and hydrochloric acid will do it. And that's because of this very favorable Lewis acid base reaction with chlorido ligands here, forming a stable complex.
So is that 4H pluses?
Yeah, 4H pluses here. Aqua regia. And so aqua regia will dissolve it. So those are the types of things we try. Now, let's look at the next example. This is going to be chapter 15. So typically what we do in chapter 13 is just, we're given something. Let's look at the formation of NO. And we're going to use this reaction. So we're going to take our nitrogen gas and react it with our oxygen gas. And this is going to form NO gas here. And what we want to do is we want to figure out what is our delta G. So first off, we're going to do it the easiest. Delta G under standard conditions at 298 Kelvin. That'll be the easiest. So the easiest way of doing that is by looking at the delta G naughts of formation. The delta G naught of formation of N2 is equal to what? 0. That's because formation reactions. Formation of 1 mole of N2 from N2, 1 mole of N2. And so we're going from 1 mole of N2 to 1 mole of N2, no energy change. The same thing with O2, 0 kilojoules, 0 kilojoules. NO is not 0. So nitric oxide, the formation, delta G of formation is defined per 1 mole, but here we're forming 2 moles. And so it's going to be twice the amount of energy. And so let's take a look at delta G of formation for NO. Which is going to be the second column here, 86.55, right here, kilojoules per mole. Is this popping up here? What is this? Delta G's of formation, delta H's of formation are always per 1 mole. Since we have 2 moles, we'll have to double that. And so 180, or 160, 172, 173.1 kilojoules. Positive. In the grand scheme of things, a plus 173 is hugely unfavorable. Oops. I lost the page, and I think I'm just about out of time here. A plus 133 okay is practically all what? All reactants, very little product. We could get a better idea if we look at K. I was looking for the delta G versus K chart, which I closed, but it's okay because we're going to calculate K anyway. K is just equal to E to the minus delta G naught over RT. This is
At 100, it's about 3.0 times 10 to the negative 18.
yeah, okay. So this is going to be even smaller than that. Yeah. All right, I'll stop here since I'm out of time. But am I out of time? Yeah, 2:30. Yeah, that's right.